So we are going to work today on introduction to functions. So inside of this yellow box, you can see a very kind of mathy type description of what a function is. However, truly all you need to know is that the x values cannot be repeated. And that is how we can determine that something is a function. So let's look at just some finite sets using a mapping diagram. So when I look at example number A, I see that every single one of these arrows maps an x value to a y value. Okay, so there are no x's that are repeated. If we were to create ordered pairs, it would just be 4, 1, 6, 3, 8, 4, 10, 5. Okay, and so we say, yes, that's a function. However, if we look at B, you can tell right away that the 6 is being mapped to a 4, but it is also being mapped to a 3. If we were creating ordered pairs, we would have right there 6, 4 and 6, 3. The 6 being repeated, my x value being repeated. So this is not a function. What do you think about C? Give you a minute to think about it. When you look at C and you look at your x values, you can see that the 5s are being repeated. So it is not a function. Rather easy way to find out whether a set is a function or not. Well, that's very simple for a finite set. But what do you do when you have an infinite set? Well, that's where we have what is referred to as a vertical line test. Not a hard thing to do. We just go ahead, look at our function. Our function is defined by the line, okay, by the graph. And all we're going to do is draw a vertical line through that graph. It doesn't matter where you draw it, okay? When we draw that vertical line, as long as we are only going through at one location, going through the graph at one location, then it is a function, okay? For B, example B, we've still got a vertical line, but it's going through our graph in 2 locations. And so that means it's not a function. Okay? Not hard. For C, even though C is kind of a crazy graph, it doesn't matter where you draw your vertical line. It's only going to intersect that graph in one location. And so this one is a function. All right. So now that we know what a function is, I do want to clarify something. A function is also a relation. Hang on. So one of the things that I want to look at now is function notation. So it's what are all the symbols that we use in order to define that function? That's what we're talking about right now. And so we are looking at f of x. That's how we say this. So f, and then in parentheses, x, the way we say that is f of x. And f is simply the name of the function. This becomes very helpful when you're developing a mathematical model to be able to name your functions. Let's say, for example, we have a very basic business model. So it maybe you're looking at revenues and expenses, trying to figure out what the profit is. So you might call your revenue function R of X, your cost function C of X, and if you subtract those two functions, it would give you your profit function P of X. Okay, so that's how naming the function can be helpful. X, okay, is the input value of the domain. So what we've got here is you've got your inputs, and your inputs are always your X values or your domain. And that is going to go inside, and then you're going to have a rule. For this example that we have right here, our rule is 6x minus 3. That means you take your X value, multiply it times 6, subtract 3. And then after you're done with that, you will get an output or a Y value. That's just how your function works. Inputs, apply the rule, outputs. So one way of thinking of this f of x is that is the same thing as y. So f of x is exactly the same thing as y. So the nice thing about this is we're going to be able to apply algebra when we're working with these functions because it's just like a y value. All right, let's go ahead and evaluate some functions. So when we're evaluating our functions, this right here, f of -1, is asking us a question. It is saying, if x equals -1, what is y? That's the question. So f of -1, we're going to go to our function and we are going to input a -1 everywhere where we see that x. So this is going to be 2 times -1 squared minus 3 times -1 plus 1. So this is going to be 2 times 1 because -1 squared is 1. And then plus 3 because a negative times a negative is positive plus 1. So that just becomes 6. So we would say that f of -1 is equal to 6. So when x is -1, y is 6. Now, that should feel a lot like an ordered pair to you. We know our x value of -1 and the corresponding y value is 6. Okay. All right, let's do the same thing with 0. So if we go ahead and substitute a 0 into our function, we would have 2 times 0 squared minus 3 times 0 plus 1. Or f of 0 is equal to 1. Okay, last one. Let's look at f of 1/2. I'm going to substitute a 1/2 in. So it'll be 2 times 1/2 squared minus 3 times 1/2 plus 1. Remember, order of operations tells us that we need to apply our exponent before we multiply. So this is going to be 2 times 1/4 minus 3/2 plus 1. Well, anytime I have a fraction times an integer, I put that integer over 1 so that when I'm multiplying, I can reduce. Okay, that makes life a little bit easier. Now I have common denominators, so I'm going to have 1/2 minus 3/2, which is a negative 2/2, plus 1. Well, negative 2/2 is just negative 1 plus 1. That whole thing equals 0. So f of 1/2 is equal to 0. Well, what happens now when I have an expression instead of just an integer? Not a problem. All we're going to do is we are going to substitute in just like we were doing before. And so this is simply going to be f of t plus 1. So that t plus 1 is going to be substituted into our function, or the rule part of our function, okay? So this is going to be t plus 1 squared plus 3 times t plus 1 minus 2. Well, this t plus 1 squared, that's just a binomial squared. So I can go ahead and create a trinomial that is also a perfect square trinomial. It's the same as t plus 1 times t plus 1. So that's going to give me t squared plus 2t plus 1. Okay? Plus, now I'm going to distribute this 3, so I get 3t plus 3 minus 2. I'm almost done. I'm going to go ahead and combine like terms. So I have t squared. I have to combine my two t's to give me 5t. Plus, now I'm going to combine 1 plus 3 is 4, minus 2 is 2. So the function f of t plus 1 is equal to that trinomial. I'm not going to come up with just a single number as my answer. This is my answer. Okay, I'm going to keep going here. So, what if we actually have a function that doesn't look like an equation, but actually looks like a graph? So that's what we have here. This blue line is our function. This is our f of x. Okay? So the way this works, so for problem A, the question that's being asked is, if x equals 1, what is y? So in order to figure that out, I go to 1 on my x-axis. I draw a line a vertical line until it intersects with my graph. It intersects at this point, which is 1, 2. It's the ordered pair 1, 2. And so my x value is 1, my y value is 2. So f of 1 is equal to 2. Okay? All right. For B, we want to know if f of 40 is positive or is it negative. All right. So our function is still f of x. Well, at f of 40, that's saying x is 40. We're not looking for a value for y. I want to know, is y positive or negative? That's what it's asking. So I know that 40 on my graph is going to be somewhere way off the chart, okay? Somewhere. I know that my y value, okay, because of this arrowhead, I know that I am going to be in this fourth quadrant. And in quadrant number 4, my x's are always positive. My y's are always going to be negative. And so it doesn't matter what the value of y is, it's somewhere down in that fourth quadrant, and it is going to be negative. All right. Question C looks the same, but it's not. It's very, very different. So this is asking actually the opposite question. This is saying if y equals 2, what is x? How did I get that? Well, remember, f of x is the same thing as y. So that's saying y is 2. And x has not been identified. That's what I need to figure out. So I'm just going to go right here to my function. And at my y value of 2, I'm going to draw a vertical line. That is right there, y equals 2, okay? And I see that this intersects with my graph in actually 2 locations. It's going to intersect at negative, when x is negative 2, and also when x is 1. And the ordered pairs right there are going to be negative 2, 2, and 1, 2. Okay, so you can see that the y's are in both of those ordered pairs are 2. And my x values, I have 2 x values. So I would say x is, and I'm using my set notation to show that the solution set is actually going to consist of negative 2 and positive 1. So the squiggly brackets, that just shows that it's a set. In this case, that would be my solution set. All right. Last, let's find the domain. So remember, when we're looking at the domain, we are looking for my x values. That's what our domain is. So we're going to start with the idea that a domain is going to include all of my x values from negative infinity all the way to positive infinity, everything in between, all real numbers from negative infinity to positive infinity. I have 2 exceptions. 2 times when I need to exclude some of my x values. My first exclusion, okay, it's when the denominator of a fraction is 0. So that would be when I might have something like this, where my x value is going to be in the denominator, and if I substitute a 0 in for that x value, I would get an error, okay? I can't define my y when my denominator is a 0 in a fraction. My second exclusion is going to be when a square root function is negative. So if I have a function and that x value underneath that square root sign is negative, then my y value cannot be defined. All right. So let's see how this is going to work. So the first thing that I notice with example number 6 is that I have an x value that's in the denominator. So the way I'm going to find my domain, how to find my, what I'm going to find first, I'm going to find how to find my exclusions to the domain. So I'm going to set the denominator equal to 0. So in this case, it's going to be x minus 7 equals 0. I just solved that. I add 7 to both sides, and I get x equals 7. That is an exclusion. Okay? That means in my domain, x cannot be equal to 7, because if I substitute 7 in for x, I'm going to get a 0. Not allowed. All right. So then what I'm going to do is just graph this. That's the second thing I want to do. So graph with exclusion. So I'm going to go ahead and I'm going to identify 7 and I'm going to put a big open circle there. Everything to the right, that can be part of my domain. Everything to the left, that can be part of my domain. Now I'm going to use interval notation to describe the domain. Okay, so that's going to be, my first part is going to be negative infinity to 7. I use rounded parentheses because 7 is excluded, not part of my solution set or my domain. And then I'm going to use a union symbol. I'm going to start back up with 7 and go to positive infinity. That's how I describe my entire domain, showing that 7 is excluded. Okay, let's go ahead and look at example number 7. So for example number 7, I'm going to go ahead, start exactly the same. I see that I have an x in the denominator. So I'm going to set my denominator equal to 0. I am going to add 4 to both sides. So I get x squared is equal to 4. So now I think about this. What number can I raise to the second power that's going to equal 4? Well, there's 2 of them. I can take 2 and raise it to the second power. That's going to be 4. I can also take negative 2, raise it to the second power, and that'll be equal to 4. So that means I have 2 exclusions. X cannot be equal to 2 or negative 2. Okay. And so I'll make a little room here. So those are my 2 exclusions. So if I go ahead and graph that, I'm going to put a negative 2 and a positive 2. And I'm going to put an open circle at both of those numbers. And I'm going to shade everything to the left, in between, and to the right. So now as I write my domain, it's going to have 3 intervals. So I'm going to go from negative infinity to negative 2, parenthesis. Use a union symbol to join the next interval. Negative 2 to positive 2. Join the third interval which is positive 2 to positive infinity. There we go. Okay. Let's look at number 8. Number 8 is an interesting example. So with this one, let's go back to how we define our domain and our exclusions. Remember that our domain is all real numbers from negative infinity to positive infinity, unless you have the variable in the denominator or there's a square root and the variable is under the square root. That's the only time you have to worry about exclusions. So the question is, do we have a fraction? The answer is no. Then we ask, do we have a square root? The answer is no. So that means there are no exclusions. And so our domain is simply negative infinity to positive infinity. We didn't even have to do any calculations. We just knew that. Okay, let's look at number 9. So number 9 looks a lot like number 7. Okay, we see that we have a variable in the denominator. Okay, let's go ahead and start the way we started before. So I'm going to take x squared plus 9, set it equal to 0. I take my denominator, set it equal to 0. Notice through all of this, I completely ignored the numerator. The numerator, even if there was a variable in it, has nothing to do with defining your domain. You only focus on the denominator. Okay, so now I'm going to solve this. X squared equals negative 9. So I ask myself, what number can be squared to equal negative 9? If you're a little puzzled by that question, that's fair. The answer is there isn't one. There is no number that you can raise to the second power that's going to give you a negative. If I try and take 3 and raise it to the second power, I get a positive 9. If I take negative 3, raise it to the second power, I'm still going to get a positive 9. There's no way I can take the same number, multiply it times itself to get a negative. So what does that mean? It means there are no exclusions. I don't have to worry about getting a negative 9 with that x squared. And it's only a negative 9 that is going to give me a 0 in that denominator. So that means my domain can be anything from negative infinity to positive infinity. That one you might have to kind of ponder a little bit and think about a little bit longer. Maybe one of those shower thoughts. Okay? All right. So now let's go to square roots. How do we write the domain for something that's a square root? So instead of finding the exclusions when we have square roots, we're going to go directly to find the domain. Okay? And what we're going to do is we are going to set the radicand, wow, that's a fancy word, into an equality greater than or equal to 0. Well, what is the radicand? The radicand is whatever is underneath that square root symbol, okay? And so in this case, it is going to be x plus 5. So what this is saying in words, it's saying that, okay, the value of the radicand, okay, whatever's underneath that symbol, the square root symbol, is going to be positive, okay, or equals 0. And either one of those things are fine. We're fine, okay? So going back to solving this, I would have x is greater than or equal to negative 5. Okay, so right here, if I substitute a negative 5 in for that x value, I would get the square root of 0, and that's fine. If I substitute a number that is larger than negative 5, so let's go ahead and let's just try negative 2. Negative 2 plus 5 is going to give me the square root of 3. That's fine. Let's go ahead and substitute something that is smaller and see what happens. So how about a negative 10? Negative 10 is smaller than negative 5, and that's going to give me a negative underneath my radical sign. And that's not allowed. That's excluded. It can't be part of my domain. And so that is why anything that is smaller than negative 5 doesn't work for the domain. So if I go ahead and shade this in, I've got negative 5, and negative 5 is included, so I'm going to put a square bracket and everything to the right. Or you could have just used a filled in circle. Doesn't matter either way. But my domain stated in interval notation is going to be square bracket, negative 5, comma, infinity, parenthesis. That's the domain.